During this presentation, we have talked about Stark effect. Stark effect is an optoelectric phenomenon. Suppose the source of light emitting light spectrum is placed in an electric field. The original spectral line is separated into multiple components. The phenomenon of splitting of a spectral line into numerous components when it is placed in an electric field is called Stark effect. If you think about a hydrogen atom which contains a positively charged nucleus and an orbiting electron, inside the nucleus one proton is present, it has no neutrons. The potential energy of hydrogen atom is V of R equal to minus ZA square by R. Here is Z equal to 1. So V of R equal to minus E square by R. Here the potential is spherically symmetric in nature. Suppose the potential is the function of R only, then the potential is called as spherically symmetric. If you place a hydrogen atom in an electric field, the energy of the electron can be changed. Consider a hydrogen atom subjected to an electric field of strength F and is acting along the Z direction. The electric field is acting along the Z direction. The force acting on the electron is minus E into F. Therefore, the new energy of the electron is minus E F Z, which is equal to minus E F R cos theta. Since the potential is spherically symmetric, the value of Z equal to R cos theta. So this is a new energy of the electron if the hydrogen atom is placed in an electric field. The Hamiltonian is H0 plus lambda into H1. Here the H0 is unperturbed Hamiltonian. Lambda into H1 is our perturbed Hamiltonian. The total Hamiltonian H is equal to H0 plus lambda into H1. In the present case, the unperturbed Hamiltonian H0 is minus H cross square divided by 2m del square minus E square by R. H equal to T plus E minus H cross square by 2m del square plus V of R. Here the potential value is minus E square by R. This is our unperturbed Hamiltonian. Whereas the perturbed Hamiltonian is minus E F R cos theta. This is our perturbed term. Here the parameter lambda equal to unity. If you place the hydrogen atom in an electric field, the energy is changed. According to the theory of perturbation, the first order energy correction is given by the formula. The expectation value of H1, the value of E1 is expectation of H1 in the ground state. This is equal to psi 0 star H1 psi 0 into beta. This is the value of first order energy correction. We proved the same in the perturbation theory. For the ground state, of hydrogen. For the ground state of hydrogen, n equal to 1. If n is equal to 1, value of L equal to 0. If L is equal to 0, m is also 0. L1 to you, for the given value of n, L can have 0 to n minus 1 values. Suppose the value of L is given to you, m can have minus L to plus L values. For the ground state, L equal to 1, L equal to 0, m equal to 0, then the wave function psi n L m equal to psi 1 0 0. This is our ground state wave function. The general formula for psi n L m equal to R n L of R y L m of theta comma pi. YLM of theta comma pi is called spherical harmonics. This is our radial part. Here psi 1 0 0 equal to R1 0 of R y 0 0 of theta comma pi. From the problem of hydrogen atom, we have arrived at the value of psi 1 0 0 as 1 divided by pi a 0 cube inside the root into e power minus r divided by a 0. This is the value of psi 1 0 0. Since the potential is spherically symmetric, the parity is taking place its vital role. Here, the potential is spherically symmetric. Here, the potential is spherically symmetric. The wave function can have even or odd parity. According to the value of orbital quantum number, the parity is justified. In general, the parity operator pi is given by the formula minus 1 power L. If L equal to 0, then pi equal to minus 1 power 0, which is equal to plus 1. Here the parity is even. If L equal to 1, pi equal to minus 1 power 1, which is equal to minus 1. Here the parity is odd. To understand more about the parity operator, consider the wave function psi of x, y, z. if pi is the parity operator, then the parity operator changes the sign of the function into the coordinates x, y, z into minus x, minus y and minus z. If there is no change in the sign of the function, even though the coordinates x, y and z are changed into minus x, minus y and minus z, the parity is even. On inversion of coordinates, if the sign of the function is changed, then the parity is said to be odd. See here, pi into psi of x, y, z is equal to psi of minus x, minus y and minus z. The parity is even. On inversion of coordinates, if there is no change in the sign of the function, then the parity is said to be even. On inversion of coordinates, if the sign of the wave function is changed, psi is changed into minus psi, then the parity is said to be odd. The wave function describing the even parity are called symmetric wave functions. The wave functions described by odd parity are said to be antisymmetric wave functions. In our case, we are using the wave function psi 1, 0, 0. This is called the ground state wave function. In the ground state, the value of L is equal to 0. Therefore, the parity is equal to minus 1 power 0, which is equal to plus 1. Anything but 0? 1. Here the parity is even. The ground state wave function is described by even parity. Now we have to prove that the first order energy correction is 0 because of even parity. Let us proceed. According to the theory of perturbation, the first order correction for energy is E1 equal to psi 1 0 0 star H1 psi 1 0 0 beta. Here psi 1 0 0 equal to 1 divided by pi a 0 2 inside root e power minus r divided by a0. Then h1 equal to minus c f r cos theta. Then beta equal to r square sin theta d theta d pi into dr. Now the first order correction E1 equal to triple integral of 1 by pi a0 cube inside root e power minus r divided by a0 minus e f r cos theta. This is the value of h1. Then once again pi a0 cube e power minus r divided by a0 into r square sin theta d theta d pi into dr. This integral limit varying from 0 to infinity. Take this minus e f divided by pi a0 cube outside. This minus e f divided by pi a0 cube inside the root into pi a0 cube inside the root, that is equal to pi a0 cube without root. Then r cube, r into r square, r cube e power minus 2r divided by a0, e power minus r by a0, e power minus r by a0, e power minus 2r by a0 into dr. Then integral limit vary from 0 to 2 pi into d pi. Then integral 0 to pi sin theta cos theta d theta. This is the first order energy correction term. We know that the value of integral sin theta cos theta d theta, limit varying from 0 to pi, equal to 0. We know that integral sin theta cos theta d theta, limit varying from 0 to pi, equal to 0. So substitute this integral equal to 0, entire thing is vanished. Therefore, E1 equal to 0. First order correction is equal to 0. There is no first order Stark effect in the ground state of hydrogen atom. Therefore, for non-vanishing perturbation term, the parity should be odd. This is the conclusion we arrived at in the case of ground state of hydrogen atom. There is no first order Stark effect in the ground state of hydrogen atom. If n is equal to 1, we would expect the Stark effect. We would expect the splitting. This is due to the even parity. In the case of ground state, that is psi 1 0 0, the value of n is equal to 0, then parity minus 1 power 0 equal to plus 1. The parity is even. If the parity is even, then the contribution corresponding to the wave function to the energy term is 0. Therefore, for non-vanishing perturbation term, if you want to get the energy correction term, the parity should be odd. But in the case of ground state of hydrogen atom, the parity is even. Therefore, there is no first order Stark effect in the ground state of hydrogen atom. Next, we have to study the Stark effect in the first excited state, that is n equal to 2 state. We will continue the same in the next lecture. Thank you.